Hi all. This is a video. It's for the Friday lecture. It talks about in more detail about some topics related to last week that you might find useful, and they're specifically related to some examples and theorems on open and closed sets. So this supplements the discussion that we've had so far and gives more examples for you to work from. So one of the concepts that I want to define for this lecture is the idea of a closure. And there are different definitions that you'll find in the literature, but using the terms that we have defined so far, you can give two definitions. All the points x in your metric space x, so we have some background metric space that we're using. All the points x such that x is adherent to E. And opening up that definition of adherent, it's all those points in X such that no matter what radius you take, and this has to be positive, then the ball of radius R intersected with E is not empty. Okay, some examples. Now, if you take this set, some of you have seen this in the discussions and elsewhere. So this consists of, we're taking all the points with distance to origin less than or equal to 1, and with the first component being strictly positive. So the y-axis is not included, and then we get, otherwise we get this semi-open disk. Now, adherent points are all those that touch it, so that would be all these points on the axis, including everything else. So the closure in this case would be equal to all those points x, y, such that x squared plus y squared is less than or equal to 1, and the second inequality we turn into bigger than or equal to. So this answers the question, what is the closure of E? That is E bar. And one could prove that this is a indeed the closure. Okay, so we need some tests to test and some properties for this. So first of all, if you take any set E in a metric space, then E bar, or E's closure, this is sometimes read as E bar, is itself closed. So this is the first claim, say 0th claim in this statement. And then other properties are if X is in E bar, if and only if for every ball, the intersection is not empty. This is the definition that we gave. 2, E bar is equal to E union the boundary. So this is sometimes you'll see that a boundary of E in some contexts. And third one is that E bar is the complement of the exterior. And the final one is that the closure is the smallest closed set that contains E. So this last statement means the smallest closed sets containing and well, why is that justified? Well, first of all, that set is closed, as we will show. And if you have any other set that contains E that is also closed, then F has to be bigger than E bar, that is, it contains that. That's the definition of being the smallest closed subset containing E. This is similar to the smallest upper bound. It is an upper bound itself, but smaller than every other upper bound. Okay, so let's go over the proof. So E bar is closed. Well, we have to go from the definition of closed, and closed means for us that every sequence that converges to something in X, that limit point has to be in E. So we have to set up this proof. So let Xn be a sequence of points in E bar, and let X be a point in X such that limit n goes to infinity of Xn is equal to X. And we want to show that X is also in E bar. We know it's in X, but we want to show more that it's in E bar. And so to show that, we have to use the definition of E bar. So let's add some words about want. Next, we will show, or next we will verify that X in E bar as desired. To do this, fix an R positive and show that the ball radius R centered at X intersected with E bar is not empty. Well, we have to find some points inside here. And what would be good candidates? Well, the sequence, we have to use the assumptions somehow that we're making. We have a sequence converging to X, and those conveniently lie in E bar, so that's a good place to look at. Since limit X n goes to infinity of Xn is equal to X, we have that limit n goes to infinity of the distance of Xn to X is equal to 0. This is equivalent to that. It's the definition of convergence. So there exists some capital N such that for all n bigger than or equal to capital N, distance Xn to X is at most R. So we're using the definite convergence, epsilon and R here is positive. So eventually they're close enough. So for all n greater than or equal to n, we have Xn in Bxr, because that consists of the points that are within that distance, and Xn in E bar by assumption. So Xn is in the intersection because it lies in both, and therefore the intersection, because it has a point, is non-empty. We're done with the first part. Okay, so this set is indeed closed. Now, we won't show quite all of these claims. I'll give some outlines that you can use. So 1, we have given the definition of the set. So 1 is really the definition that we gave. Now, 2, I've written here, 2 means that we wanted to show that E is equal to E bar is equal to E union boundary of E. And I'm saying that we could use 1 or use the definition specifically. So, well, X, we have to show 2 things, that E bar is contained in E union boundary of E, and then the converse, that is E union boundary of E is contained in E bar. Okay, so case this, well, let's fix an X inside E bar. then for all r positive, bxr intersected with E is not empty by definition. Now, either there exists some radius, positive, such that bxr is actually contained in E, or this does not hold, or this does not hold, because every claim is either true or false. So if so, well, then bxr is contained in E, and x is contained in bxr, so x is in E, meaning that x is in E union boundary of E. Okay, great. That's an easy case. So suppose this was false. If false, well, that means that for every radius, r positive, we don't have this. It's not a subset of E. We have that bxr intersect E complement is not empty. But since also bxr intersect E is not empty, by being in E bar, this means that x is actually in boundary of E, and then proof. But being in the boundary means that, so x is in boundary of E union E as desired. Either way, we get that it's in this union. It's just a different part of the union. The second part is very similar to this, but I will leave that to you. Okay. So we did this one. This was the definition. 2 we did. And I want to say something about 4. Well, yeah. Yeah, about 3 and 4. 2 we didn't completely prove, but 3 and 4, let's say a little bit about. Okay, so I want to say that E bar, we want to show that E bar is the same thing as exterior of E complement. Now you could proceed as in 2 to show that E bar is contained in the complement and the complement is contained in E bar. But this time, let's go a little bit more directly. Let's write these out. So x is in E bar is equivalent to saying, by the definition, that for every r positive, bxr intersects E in a non-trivial way. Well, this is the same thing as not that there does not exist an R so that bxr is contained in E complement. Because every ball intersects E in non-trivially, then no ball is contained in the complement. But that this is not true means that x is not an element. So then we have not x in exterior, which is the same thing as saying x is in the complement of the exterior. Now writing it this way is more convenient because these are all equivalences. And it shows that you can go both ways in this proof. So in this case, this would be a complete proof. Now, I'd rather you add some words to this than just write these symbols. But in the interest of saving a little bit of time in this video, I just wrote that outline. So that's case 3, that the closure of E is the complement of the exterior. And then our final thing is that smallest closed set containing E. So we want to show that if F is closed and E is contained in F, then E bar is contained in F. Well, let's set this proof up by assume F is closed and that E is contained in F. Well, then if we want to show that E bar is in subset of F, so let's take an element in E bar, and we have for every positive radius that the ball BXR intersects E in a non-empty way. Okay. Well, then for every R positive, the ball of radius BXR also intersects F in a non-empty way because we're making the set bigger. So here we're using since E is a subset of F. Well, this works for all R, and I want to somehow use the fact that it's closed. I could quote a theorem here that then X is in F, but let's do it more directly. So for every natural number, I'll use this condition for smaller, this holds for all R, so I can use it for very small radii. Then there exists an xn in the intersection bxr at bx1 over n with F. So because this is non-empty, I can choose a point. Now, limit n goes to infinity of xn is equal to x. This we have done many times. You should expand this, but I will leave it for now. So limit xn is equal to x, and xn is contained in F because it's contained in the intersection. So X is in F because F is closed. But this is exactly what we wanted to show. We wanted to show that every element in E bar is an element of F, and we are done. Okay, so mostly this is unwinding the definition. These proofs usually have three parts. You state your assumption clearly, you massage the definitions a little bit, and then you conclude with what you want to say. It would be good for good practice to add a final statement saying something like, since every element of E bar is also an element of F, then E bar is a subset of F. So, which is what we wanted to show. Now, one has to be a little bit careful with these definitions. So there are some counterintuitive aspects, and one of these is hinted as an exercise in Terence Tao's book, and it's also mentioned on Campus Wire. So we have three different sets. So one is a closed ball, consists of all the points in your big space such that distance x to y is at most r. There is another set where you take all the points whose distance x to y is at most r with a less than or equal to sign. And the question is, are these equal? And yes and no. Yes, if your metric space is Rn with the usual metric. But no, in general. Indeed, Next, we will show that C is closed. So because B is a subset of C, then by what we just showed, the closure of B is a subset of C. So B bar is always a subset of C, but they're not always equal. An example of non-equality. Example, if my metric space is just natural numbers, and if I take the ball of radius 1 centered at 0, and here let's say 0 is a natural number, so this includes 0, then the ball of radius 1 is just 0 because the distance to any other element is at least 1. My C would be equal to 0 and 1, but B bar, because a singleton is closed, would just be 0. So in this case, we would have that B bar is contained in C, but not equal. Now, some of these properties are contained in a theorem in Terence Tao's book, 1.215. I want to briefly say something about the crucial ideas that go into this proof. Not very much, though. So if we define the set that we just considered, those with distance at most R, including R, then this set is always closed. We'll see something similar to this next week when we talk about continuity. Now, a useful property is that a subset is open if and only if its complement is closed. This you use a lot of the time. And then based on this, related to this, we have properties of closed sets that are related to analogous properties of open sets, is that if you take a finite union, and crucial, it has to be finite, we get something that's closed. And if you take any intersection of closed sets, then you get something that's closed. And finally, there's a nice characterization in this theorem of the interior of the set. Like the closure, the interior has a meaning in terms of open sets. The interior is the largest open set contained in E. So if you have another open set, omega, in E, then as a subset of E, then omega is contained in the interior. So something about the proofs here. First of all, H is in your homework, so I won't discuss that now. You've also discussed it a little bit in discussion. E, the statement about open and closed and the complement, this is on YouTube in a supplementary video. If you're interested in that, you can look at that. So I will say something about C, G, and F. C, F, G, and F. We won't probably do full proofs here, but so we want to say that this is closed. Now this is something that's very important. So let's say, and that's why I will do the more full proof for this one. So fix, we have to prove that it's closed. So let's fix a sequence of points in C and an X that initially we assumed that it just lies in X, but we will conclude that it lies also in C, such that limit n goes to infinity, xn is equal to x. We want to show that x lies in C. And well, what we have to show is that the distance to x naught is at most r. Well, we know that distance of xn to x naught is at most r because xn are in C. And this is the definition of points that are in C. And we want to pass to the limit, replace the xn with an x. Well, what we get, we have to use the continuity. So for every epsilon positive, there exists some capital N such that for n bigger than or equal to n, distance xn to x is at most epsilon. And from this, so for all n greater than or equal to n, what we have, if we look at the distance from x to x naught, well, by triangle inequality, we can compare x and xn, and then xn and x naught. Well, the first one is very small, epsilon, and the second one is at most r. Now, the trick with this estimate is that we've lost dependence on n. This is something that comes up a lot with sequences. So, for every epsilon positive, we have that the distance from x to x naught, whatever it is at most r plus epsilon. So if you have a number, this is a real number that's less than r plus epsilon for all positive epsilon, sending epsilon to 0, or you could also say since epsilon is arbitrary, we have distance x to x naught is at most r, so x is in C. X is in C, not C. And this shows it closed. So this nicely combines sequences and continuity. Now, something about these other statements. Intersections being closed. I'll just give, I won't write the full detailed proof, but I will say the idea. If you have a sequence of points in the intersection, then for all these sets in your collection, xn is in fi for all n. Now, if you have limit n goes to infinity of xn is equal to x for some x in x, then since this is also a sequence in fi for each I, we get that for every I in I, x is in fi. And from this, because it is in all of these fi, this is the same thing as saying that x is in the intersection. So yeah, the idea is to use this condition for all I. Now, this is not a complete proof because I haven't said all the words, but the crucial idea is that we apply, the sequence lies in each one of these individually, and we apply it that way. With unions, it doesn't work in the same way because the sequence doesn't, every xn lies in one of these. And so they can change which one they lie in. So this actually is a little tricky to prove. You can prove it with sequences, but there is a nicer trick. Let's look, and this is often useful in things related to topology and metric spaces. If you take the union of fi, let's look at the complement. Well, the complement is now an intersection of sets of the complements of fi. So by C, fi complements are open. Finite intersections of open sets are open. So a complement is open. Now, since a complement is open, going the other way, therefore, by C again, A is closed. So this is, sometimes this is called an instance of duality. You can often prove things for closed sets by looking at their complements and vice versa, whichever you find easier. So in this case, it's easier to prove that a finite intersection of open sets is open, and this is done in that, actually also in this video on topology. But going the other way, for Closed sets is therefore easier to actually go via the complement. Again, this is not quite a full proof, but it includes many of the main ideas that are involved. Thank you for your attention for now.